In this installment, we're going to look a little bit at the definition of force in particular. So the first thing I've included here for you is a general definition. So even though physics, this is the first time you're formally studying physics, almost everyone has encountered the word force at some point in their lives, especially even at a very young age. And so there is a distinction between words that have particular meaning in our general usage and those that have a technical definition. So, and we can illustrate this by looking at just this general usage. Force, by definition, is, according to a Merriam-Webster dictionary, is strength or energy exerted or brought to bear. So it's strength or energy. Force is energy. And we know enough now to know that force and energy are completely distinct in different contexts. So what the field of physics does is has taken these common terms that have been around for centuries and has provided a very specific scientific meaning to them. The more useful part of the general definition is it's the cause of motion or change in motion. But bizarrely, it's also described as active power. And so we, of course, have learned so far that work is force times distance. So work and energy are not the same thing. And we know that power is force times velocity in terms of its general physics definition. So force itself, from a general usage definition, is not intelligible to us. The technical definition of it, and I like this one, it's any interaction that, when unopposed, it's an interaction, when unopposed, will change the motion of an object. And to change the motion of an object means to change its velocity. So those are our definitions. Now let's take a look at this scenario and see some applications. So we have children pulling with the same force. So we have our ground and our tree that I've drawn here. We have these two children here. So let's suppose now that each of them exerts a force of 2 newtons. Every child, these children look to be about 4 or 5 years old. Each of them exerts a force of 2 newtons. What we can see is there's 6 newtons on this side, and there's 4 newtons on this side. So we can clearly see then that the team on the right should win this tug of war. And so what we would then say is that the team on the right wins by 2 newtons. And if we apply vector concepts to this, we see there's plus 6 newtons in this direction and minus 4 newtons in that direction. And so we get when we add those forces up, we have the sum of the forces we get is plus 6 plus a negative 4, which is plus 2 newtons. So what is not so obvious is that if we add 2 more children, let's suppose we add another child on this side and another child on this side. Well, we now have another 2 newtons on this side and another 2 newtons on this side. So that now gives us plus 8 newtons on this side and minus 6 newtons on this side. So when we look at the sum of the forces now, we have plus 8 and minus 6. And so the sum of the forces we end up with is still plus 2 newtons. And so you can see that if we pile more and more and more forces on each side, that we have 1 on each side, keep adding 1 student to each side, that the net force or the sum of the forces will not change. It will always be plus 2 newtons if we add 1 on each side. And so that this whole system is not determined by the forces, it's determined by the net force. The winning of plus 2 newtons stays the same when we add more and more students. So if we go back to the definition about unopposed forces, we'll change the motion of an object. So it turns out there are a bunch of forces. We have this student this child and that child, their forces are opposed. The forces here with these two are opposed, leaving just the one girl in the first case. So it's only her force that is unopposed. So it's a force that when it's unopposed will produce motion. So we know this will move or accelerate to the right. But if this child were not here and we just had child 1 and child 2, child 3 and child 4, all of those forces are opposed. So if they're unopposed, there'll be no change in motion. It's only due to the unopposed force that there is a change in motion. So there's two takeaways. One is that forces don't necessarily bring about a change in motion. Do not necessarily bring about a change in motion. Only unopposed forces do. And so it may seem kind of shocking that if we end up adding 10,000 children on the right and 10,000 children on the left, still the change in motion would be due to just that one child difference. They will be perfectly balanced. There will be no change in motion. So we already see this concept of sum of the forces. Now, sum of the forces and the net force are synonyms. They mean the same things. Sum of the forces is the net force. And the result of this whole interaction up above was we had a net force of 2 newtons. And so that net force of 2 newtons will cause the whole system, the whole thing, to move to the right. It will accelerate to the right. And so we know already the Newton's second law is F net equals ma. And the net force is the sum of the forces. Now, we've previously learned that the definition of a force, technically, is the rate of change of momentum. So if we go up to this, the net force definition is the rate of change of momentum. Notice that is different than just the definition of a force. And so the net force is that unopposed part. And that unopposed part will change the motion of an object or bring about the change in velocity of an object. So if we write this out formulaically, the net force is the rate of change of momentum. And the change in momentum is mass times change in velocity. And I've reordered the pairing for the fraction, the ratio here. And so mass times change in velocity is change in momentum. And we see that the rate of change of velocity is the acceleration equals ma. Now, we've already derived that previously, but that is another 4-way equivalence that is very useful. Now, we could do a little bit of algebraic legerdemain here, or manipulation, and we can multiply every term here by delta t. So that would give us F net delta t equals delta p over delta t equals m delta v over delta t times delta t equals ma delta t. Well, F net delta t, delta p over delta t times delta t. I forgot to write that in there. The delta t's cancel. These delta t's cancel. And we've got ma over delta t. And of course, ma is delta v over delta t. So we've got m delta v twice. So what we see is this 4-way equivalence is just like our other 4-way equivalence, which is the impulse j is F net delta t is delta p is m delta v. So these two 4-way equivalences go hand in hand. They are just technically one of them multiplied by delta t gives you the other. And so that's just a little more exploration in terms of forces, the general and technical definitions of forces, the meaning of net force, a re-examination of the net force, Newton's second law, its definitions and its relationships to the changes in momentum. In the next installment, we are going to look specifically at weight, that force which is called weight.